Hi, welcome to another episode of the KieLive series. We are very happy to be here today with you to talk with a kind of different audience today, right, Porcelli?
Yeah, it's gonna be awesome, but it's a different aspect of the technology. So we'll see a little bit of behind the scenes how the magic happens when you're building Quarkus extensions and how we build this efficiency model around and probably we'll tackle also the native aspect of the Quarkus as well. So that we learn a lot today.
Yeah, what I think is good is that if you are a contributor already to the Cogito project, you can learn. If you are just curious, you can learn. If you are a developer and you want to know how generally the Quarkus extensions work with code generation, how that goes behind the scenes, this is also going to be very useful for you. So stay around. This is going to be a really, really technical live today, technical session today. And the person that we have here is directly involved with both projects, both Quarkus and Cogito. And he saw the marriage of both happening, right?
Yeah. So without much further, let's bring Eduardo to this session.
Hello. Hi,
Hey,
everyone.
Edu,
Ah,
thank you for accepting our invite to be here today with us. We are really glad that you could put all this content together to share with us. Okay, looking forward to it actually, especially for the live demos that you have that might just blow up. Will it?
Oh,
Will it
no,
not?
please, no, God.
yeah. Did
Happy
you
to
make
be
the
here.
sacrifice for the demo gods?
Yeah, that's why I don't usually do live demos. The demo gods hate me.
Uh, well, I did my sacrifice early today. I cleaned a foot of snow off all my driveway. So we got a lot of snow here today.
Oh,
And I did my sacrifice. So maybe you take this for you.
send good vibes.
Yeah.
Edu, can I share your screen so you get started? I don't want to take too much of your time because I know we can have a lot of content here. So,
Yeah, yeah,
okay.
let's start. Yeah.
Perfect. So I am already sharing your screen.
Mhm.
People on the chat, if you have any questions, feel free to share with us anytime, and we will bring your questions to Eduardo. Okay. Thank you, Edu, and good talk. We'll be on the backstage.
All right. All right. Thank you. Thank you for having me today. And thank you for joining. So, we're going to talk about Cogito and Quarkus, the marriage made on a cloud. Okay, so as Karina and Alex correctly put, today it's going to be a little bit different than usual. I wanted to do a presentation that it's open to everyone because it's not going to be, it's going to be technical, but I believe it's something that it's easy to understand for a lot of people. But I wanted to do something that could be consumed by a very different audience. So we will see. So who am I? My name is Edoardo Vacchi. I'm Italian, and with that handle, Vacchi, you can find me pretty much everywhere. I've been doing research at University of Milan and a small company called Mate. Then I joined the UniCredit Research and Development Group. UniCredit is a bank, and then I'm here. I'm here at Red Hat, where I do Drools, jBPM, and of course Cogito. And so this is why I'm here talking about that. So this is the intended audience for the talk. You could be a teammate. In that case, hey, hello. If you're a teammate, this is a presentation to let you know some bits of the code that you may not be aware about. So here's to you. You may be a wannabe contributor. So maybe you're a coder, or you're someone that using Cogito, that playing Cogito, or knows other parts of our platform, and you want to try to fix a bug or provide a feature or something like that, but you don't really know where to put your hands. So this is a presentation that will concentrate on Quarkus extensions, and this is for you. Or maybe you're just curious, and that's fine too. You just want to know, how do people in the Cogito team develop Cogito and all the magic that goes there. So it's open to everybody, basically. So first of all, when you want to take a look at Kogito, what you do is visiting github.com/key-group/Kogito-runtimes, and then you get a bunch of modules, and you're there saying, okay, now what should I do? Glad you asked. So this is our agenda. We will talk a little bit about Kogito, of course, because you're still not sick of it. And we're going to talk about what's compile time and runtime, because I'm pretty sure you already know what that is, but we're going to spend a little more words about how this is important for us. We're going to talk about Quarkus extensions, of course, and how they work with Kogito. We're going to talk a little bit about bytecode versus source code generation, because we do both, and you might wonder, why should you do one instead of the other? And my favorite part, I think I switched the list here. First, we're going to talk a little bit about scaffolding and troubleshooting, and then we're going to talk, my favorite part, about GraalVM native image compilation. So a couple of words about Kogito, but probably you've already heard about this a few times. It's our cloud-native business automation for building automation suite for building intelligent applications backed by battle-tested capabilities, of course. It's our platform where we brought the tools, the projects that you already know and love, jBPM, Drools, Planner, but we try to reimagine them in such a way that they work great in the cloud. So we support Kubernetes and OpenShift through the operator framework. We support dashboard definition through Grafana and Prometheus. For metrics, we use Kafka and InfiniSpan for persistence. And of course, Quarkus is front and center. There's one guy that is missing from one slide because we're not going to focus on that, but we do support Spring Boot. So there's support for a more traditional cloud framework, if you will. Now let's talk about compile time versus runtime. I'm pretty sure you know what compile time is and what runtime is when you speak about developing applications. Compile time is what you do when you build your application, and runtime is when you execute. But why it is important for us? So when we think about compile time, we usually think of what we do when you write applications. But a thing that I want to bring to your attention is that you could find a compile time phase even in programs where you wouldn't suspect there is one. For instance, if you think of the programs that you have written along your career, you will notice that there is always some kind of pre-processing phase where you prepare your program for execution. After you do the pre-processing, then there's actual process execution. There's actual execution phase, right? So the idea is that you can logically find these phases, and sometimes you will actually do this preparation in a separate step of your program, and sometimes we will do it along the way as your program runs. But if you are able to distinguish between these two phases, you can have great benefits. Let's see a couple of examples. So for instance, one thing that we often do when we develop application is loading configuration at startup time. So basically your application starts, you scan your file system, or you look on your file system or your class path for one specific file to be present. You read that file, you parse that file, you validate that file, and then you have the parameters that you will use to execute your program, right? And well, you could do this, usually do this at the beginning, because if you did it every single time during the execution of your program, you will waste time and resources. So you just do it once. Now, the thing that I want you to think about is your configuration really changing across runs? This may be true when you're developing your application, but when you deploy your application to some server, to the cloud or whatever, then you don't really want your configuration to change over time at runtime. Basically, what you want is something that doesn't change over time. And this is just as true when you think about runtime dependency injection. So the Java dependency, the Java framework that we are traditionally accustomed to, at least in the last decade or two, it's something that when it starts up, it loads, it scans the class path for classes. And along the way, it will find classes that are annotated somehow. And if those annotations are useful, then it will take note of those annotations, and then actually start the application. And through reflection, it will instantiate classes and make it available to the application. And then finally, your application, your main logic will run. So all of these is often and usually happening at startup. And this is mostly convenient and useful if your application changes a lot. And this may be during development time, or it was a bit truer when we used to deploy our application in application servers, because in application servers you had services to which you connected to at runtime. And the idea at the time was that the backend to those services could change. And that's why you didn't want to, be specifically connected to your code. That you didn't want you to code exactly against that particular service, but again, a more generic interface and bundle them together at runtime. So all of this to say that today we do things differently. The idea is to do immutable, containerized, or Dockerized microservices in the cloud. So what you do is an image, and the image does not change over time. So you do not really need to load classes at runtime dynamically, because those classes cannot change. You have already all of those classes there in the image. So you don't really need runtime dependency injection. And that's why frameworks like Quarkus or other frameworks like Micronaut which probably was the one of the first to bring this idea, they do a lot of code generation instead of doing runtime reflection. And in fact, code generation may be the solution to a lot of these problems. So you can process configuration and generate code with configuration options preloaded. So you just load code with all the flags that you need at runtime. And you can resolve dependencies at compile time and just generate wiring code. So factories, a startup method, initialization methods, and so on and so forth. And in fact, there's not only Micronaut. Among the state of the art, there's Dagger 2, which is a framework from Google, which does dependency injection. And if you know Juice, probably you are already familiar with the syntax. What you do is that instead of using annotations and instead of using you do use annotation, but you do not only rely on annotations, and you do not use configuration files. You use this sort of DSL, Java DSL, and you specify through that the heater interface will bind to the electric heater implementation. And as you can see, there's an annotation for providing factories as well, provides. Now, what happens under the hood is that Dagger is implemented as an annotation processor, and what it does is generating code. And this code is more or less like this. These are examples that I took from a Google presentation that you can find online. I think I might have missed some links at the end, but I will share them if you want. Anyway, you can Google for it, and you will find that the code is very readable. It's code that you will write by hand, except maybe the $$ here, but basically it's code that you could write. So that's the basic idea with Kogito CodeGen. So the code generation that we do is, in general, code that, in some sense, you would write. But we do that for you. So let me show you a little bit of code here. So yeah, this is some example that you may be familiar with. This is a DMN, and Well, what I wanted to show you here is that the classes that we generate here are basically well, these are classes, but there's also generated sources here. And as you can see, this is the code that we generate. And if you open it, it's not that dissimilar from code that you could write by hand. All right. So let's check the presentation. There we go. Right. There are at least, I would say, 4 categories of files and code that is being generated by Kogito CodeGen. We won't go totally into the details of that today, because there will be a follow-up presentation where we will talk about that. But this is just to give you a mind map of some sort. The slide here shows these as if they were a sequence, but they're not really a sequence, not right now at least. So what you do is providing assets. So those could be DRL files, BPMN file, DMN file, PMML file, or whatever. And what we do is generate this code. We generate what I called pre-built assets. So we pre-analyze and validate and compile, in some sense, these assets that you give and generate some code. In the case of Drools, this is called the Drools canonical model, for instance. BPMN uses something that is called the BPMN canonical model, the Fluent API. These are all internal details, but this is what happens under the hood. Then we generate something else. We generate REST and event handlers. So these REST and event handlers are the things that that respond to requests that come from outside and produce the results. And then we also generate wiring code. We generate code for composing these things together and to let Quarkus or Spring know that they are there. So glue code in some sense. And these are examples and file names of things that we generate. But this is very much something. It's an implementation detail. So I'm just throwing this out to you just to give you an insight. But do not rely at all on this, because this is subject to change, and it won't most certainly change in the future. In fact, all this code generation part, the Kogito CodeGen module in our code base, I'm not going to go into the details of that because we are in the middle of a big refactoring of that, and that's why I cannot go too much into that. So what are the modules that consume Kogito CodeGen? There's the Maven plugin and the Quarkus extension. So let's get a look at the Maven plugin. So as I said, I wanted to show you some little bit of code to give you some way to. What's happening here? Sorry. There we go. To give you a way to navigate.
Hello.
Hello.
Can you please increase your font size?
Oh, yeah, sorry.
Thank you.
How do you do that there? Presentation mode. Yep. That should be better.
Way better. Thank you.
So I wanted to give you a way to understand where this file is, but basically it's in the Maven plugin, as you can see. Well, no, you can see that. Anyway, it's in the Kogito Maven plugin module. And I'm not going to go too much into the details of that because this is mostly used by Spring Boot. But the thing that you have to know basically is that this is really part of Kogito CodeGen, and this is using. I mean, this is the code that you see here is part of Kogito CodeGen, and in fact, what the Maven plugin and the Quarkus extension do in most cases is just delegating to Kogito CodeGen, and that is all. And that's why we have a common core. And a common set of classes that are reused across the different interfaces, the Maven plugin and the Kogito Quarkus extension. So let's switch back to the presentation. Oh yeah, you can see here the path. So it's Cogito Maven plugin. Now, about the Quarkus extension, which is what we're going to talk a little bit more about. The Quarkus extension you can think about as a code gen-based framework. It's a framework that lets you develop code generation in some sense. And it plugs into the code gen mechanism of Quarkus, and it allows you to produce more code. In general, it just allows you to plug into this mechanism and see what happens. But you can also produce more code and communicate this to the engine so that the Quarkus engine is able to use it. All right. Yeah. Let's switch back to the code. And it's come on, you know that one. Well, it's Cogito Asset Processor anyway. Cogito Asset Processor. There you go. So this is the entry point to our Quarkus extension. And I just want to show you that there's something familiar here. Cogitable concepts. These are things that are also in the Maven plugin. And that's not by chance because they're sharing a lot of the code. But let's go through it a little bit more slowly. Things that you may notice here. There's some injection points. And there's this other annotation build step. You may notice here this has no parameters. It's just returning something. And the same for this one here. And there's this other one here that it's a bit more complicated. You will see it has a lot of parameters, and these are build producers. And there are some other things that happen here, some logic that we will see in a bit. Okay, so what's happening here? Oh, another thing that I wanted to show, of course, it's that there are two parts in the Quarkus extension: the deployment part and the code. Can you presentation mode? So I just wanted to show that there are two parts in the Quarkus extension here. There's the deployment part and the runtime part, and we will mostly focus on the deployment part. Okay, let's switch back here. So this is the code that you just saw, and so you might wonder what build step is. So build step, it's an annotation that usually annotates a method. Method parameters work as requirements for that method, while the return type, it's kind of the provided result. You can actually think of it as something that you may be more familiar with, the CDI produces method or Spring factories for beans. So what happens here is that this method gets called automatically when the dependency, when the thing on the return type, in some sense on the left hand side, it's required on the right hand side. So it's required by someone else. So I will give you an example in a bit. The twist here is that you can also return more than one element, so you can actually provide more than one type. So let's give a look to what's here in the yellow rectangle. What's happening here is that you're acquiring this class, some other build item, to be provided to you in order for you to generate this other class that's called some build item. And these are both beans, like Java beans, like CDI beans, or Spring beans. The difference here is that in Quarkus, you cannot just return an arbitrary bean. You have to use some specific types. And in this case, these are called build items. They're a very simple interface, and it's almost almost only a marker interface, because it's just a bean. It's just marking that this can be injected by the Quarkus engine. Now, if you're familiar with make files or end files or other build systems, what happens there is that you are defining a chain of dependencies. And this chain of dependencies is automatically resolved depending on what you ask the build system to do. For instance, in this case, this make file will work like this, because the all task will invoke recursively the foo.o task if the foo.o file is not available. And the foo.o file will require the foo.c file and compile that file. And the same for bar.o, which is invoked if the bar.o file is not available. And in particular, if you write it like that, make will look at the timestamps of the file on the right. So if foo.c has changed, then foo.o will be rebuilt, and so on and so forth, all recursively. So this basically entails a dependency graph. And this is what's basically happening under the hood, to be fair, in any dependency injection framework, but specifically in the Quarkus extension system. So, as I said, for build items, you can basically think of them as CDI or Spring Beans, but they are a special interface that represent things that can be produced or consumed. You cannot just inject or produce arbitrary things. They have to be build items. But there is a twist. You can also, for free, depend on a collection. Actually, this can be done even in regular.
Actually, super for free.
Yeah, actually, you can do that probably. I mean, probably you most certainly can do those even in CDI or Spring. But I mean, I believe this is relevant to stress because it means something particular for our dependency injection framework, for our dependency resolution system. When you are requiring a collection, what you're saying is, I want to have a collection of all the item of this particular type, which means implicitly that you want to be the last element that is called after all of those items are being produced. If you just put one build item, you may be called every single time one of those build items is available. In this case, what you're saying is, I want to wait once all of these some other build items have been produced, and then I want to be called. Let me switch back very quickly to the code and to the presentation mode. We go. You may notice here that this capability, it's so as you say, arity 0, so it doesn't have any arguments. This means that this can be produced without waiting for anybody else. While if I had a collection, I would have to wait for other build items to be available. In Quarkus, the reason why usually these build items do not depend on others is that Quarkus uses this information, and other extensions use this information to know if a particular capability is available. And that's why you usually want to be produced without depending on too many things at once. Let's switch back here. All right, but in our case, you might have noticed that there are build producers. Before we get these things can be mixed and matched. So you can depend on some particular build item, but you can also depend on a build producer. What a build producer is, you can think of that as a decorator for build items in some sense, but more in general, it's a collection. It's a mutable collection in a way. It's an injectable mutable collection where you can only put stuff, and through the produce method. So this means that you can return more than one item of the same type, but you can also inject more than one build producer of different types, which means that you can produce more than one and of different types. So you can have basically for free multiple return values. and you can have as many as you want just for today. Well,
Okay, finally found someone as excited as I am when presenting.
yay!
So, yeah.
Quarkus extensions, yay!
Oh my god. Okay.
All right. So yeah, that's basically it. All right. But so the goal here is not just to inject stuff and return stuff. Of course, this is useful, and it's useful if you want to write an extension that probes things around. So I want to know whether a particular capability is available. I want to produce some item just to let other extensions know that something is available. But what we really want to do in Cogito is producing code. So what we do to produce code happens inside the body of the methods. So let me switch very, very quickly to the code. But as you can see here from the preview, the real work happens in the body. So we generate code there, and then possibly we dump it to disk and to make it available for inspection and for other reasons. But as you can see here, there are multiple places when we invoke generate, when we dump files to disk, and there's a bunch of different things here, and we will get to that in a bit. But that's the basic idea. So you hook into the system through this build item injection system, and then you require items, and you build stuff, and then you generate code, and then you return build items. Okay, so how do you let the system know that and the system in this case is Quarkus? How do you let Quarkus know that some particular piece of code has been generated? You cannot just dump them on disk. Otherwise, Quarkus might not be able to find them. And this is particularly important if you're generating resources or beans. The way you do it is that basically you create a build item with the paths, or these are classes, so these are beans, so there may be different parameters depending on the thing that you're doing. But in this case, we have paths and contents. But in general, the idea is to let the system know that these things are available, and this way, Quarkus will know how to treat them as it goes further with the build. Dealing with reflection. So you might have heard about this. So you have to let the system know about when you do reflection. Sometimes you might have seen in some extensions some warning saying, I don't know about this particular class hierarchy. So I'm not sure I will be able to do reflection upon that. And that's why in the extension, we can let the system know that some particular classes that we write do not need to be scanned for reflection. And for instance, DMN context is one such one such class. There are other classes that need to be available for reflection, and we let the system know through this build item, reflective class build item. And there are other cases like this, and this is the way we communicate with Quarkus. Another interesting and important component in the Quarkus extension is Gendex. So as we said at the beginning, the previous slides, one thing that takes a lot of time, and it's not necessary for a lot of situations, is class path scanning. Because your class path is something that you usually know beforehand. You already we have build systems. We prepare Maven plugins when we do our program. So we already know all the complete set of dependencies that we have there. So we do not really have to scan and discover. That's something that an application server might need to do. But for a build, you already know all the dependencies that you have there. So what instead Quarkus is doing, it's using this dependency, this library called Gendex for Java index, basically. Gendex prepare and caches, dumps to disk a file that it's an index, and this index indexes all the classes that you have, that you tell it, and it will tell you information about the hierarchy of the classes and information about the available annotations on those classes. So you can query it and just say things like, I want to know which are the classes with the hello annotation, and it will find them for you. Or you can also say, is there any annotation of this kind available? Is there any class with this particular name available? And we use this procedure in Kogito to activate or deactivate particular feature. For instance, the add-on system currently uses this. This is interesting. This is, I think it's a peculiar feature of the Quarkus, of the Kogito Quarkus extension. We're using the compilation provider, and we're providing several compilation providers. Let me switch very quickly to the code here, and this is different from the Quarkus. This is the Quarkus extension, which is called the Cogito Assets Processor. There are other classes, but this is the main thing that gets that runs when you do Maven package, Maven verify. This is the things that runs usually. But there's another component which powers the live reload. So you might have noticed here at the beginning of this piece of code, which is the main Quarkus extension, that we check if we are in live reload mode and we return immediately. This is because we don't want this code to be run every single time a change is applied to a running program. Instead, so this is one way to do hot reload. Instead, we are using another feature of the Quarkus extension system, which is called the compilation provider. So the compilation provider, it's a very tiny interface, and there's just a bunch of methods, and the most important method is really this one, compile. It will give you a set of files and a context. The context is the class that I've collapsed here, and it's just a bin with a lot of metadata about the build that it's happening. And so the set of files is the set of files that have changed. So the thing that you see when you do hot reload, of a DMN file, for instance, you will see that a bunch of files have changed, and things will be refreshed and reloaded. So this is the component this is part of the component that does that, and we implement that interface in a few of our classes in the Quarkus extension. So this extends a common class in order to have a very little code here. This is a class from Kogito CodeGen, and it's in particular this is the bit of code that deals with BPMN and BPMN2 files. And yeah, what's happening under the hood here is that we are handling these files and regenerating the code for those files that are provided in the context that should be rebuilt. Now, another thing that I want to show you is the common class here. A thing that we do is we actually extend the built-in Java compilation provider. The fact that it's an extension, it's an implementation detail. This could be just as well a delegate. And I wanted to show you this because it's interesting. What we do at the end, we dump to disk the file that we generate here. As you can see, we dump them to disk, and then we invoke a super.compile, which means that we are invoking actually the Java compiler, the regular Java compiler with files on disk to recompile on the fly into bytecode, because Quarkus actually deals with bytecode mostly, not source code. And that's how we do it on the fly here. Okay, let's switch back to the presentation. And this is how the compilation provider works. And this is an example. This is for rules. Another thing that I wanted to show you is hot reload testing, which differs from regular tests, and that's why I wanted to show you. So hot reload tests. So what happens here is that we modify a resource and simulate Quarkus reloading that extension. This is part of the extension framework. It's not something that is custom to Kogito. And what happens here This is invoking a REST endpoint as you would usually do for a Quarkus test. But the thing that we do is that we modify source code, we change a class, and we replace some text. Then we invoke again the same REST endpoint, and what we expect is the result to change depending on the change that we did on the text file. The interesting thing here is that we're not triggering the recompilation manually. This is an integration test, so it's Quarkus that it's retriggering the hot reload procedure. And that's how you test hot reload. I wanted to show you this because this is pretty different by other tests, by other tests that you could see in our code base. Let me switch back very quickly to the presentation mode because I don't remember test names. But here in the Quarkus extension, we have other integration tests besides hot reload. And these test cases, I will show you one and switch back very quickly to the presentation mode. As you can see here, this is a regular Quarkus test. So the way you test your extension is really generally using Quarkus test. So the test that you usually use to test your applications. But the hot reload it's a bit different because it does these things. It allows you to modify source code to see if it actually reloads correctly. And this is how our integration tests work. Other integration tests, these are found in the root of the Kogito repository. It's integration test -Quarkus, test decisions, test predictions, processes, and rules. These are different integration tests. These deal with the end-to-end testing of our platform. So these are used especially when you have to test other aspects like persistence. So if you have to test against InfiniSpan or Kafka, then you most likely want to write a test and put it here and not in a Quarkus extension. All right, so we came to the bytecode versus source code debate. Sometimes the Quarkus team themselves, members of the team asked us, why are you generating source code? Why you could generate bytecode and be much faster? Well, that is true, but there are two reasons mainly. One reason, so the reason why Quarkus does bytecode is that it's faster, of course, because you do not have to compile it again. And the main issue with that is that you have to generate valid bytecode. Otherwise, the JVM will blow up at runtime. So you have to be careful. And of course, we can be careful as well. But we wanted to, in some cases, the code that we generate is a bit complicated, and will require us to generate very complicated bytecode and basically do the same work that the JavaC compiler is doing. So what we're doing right now, it could change in the future. We're generating source code and delegating to the Java compiler to do the rest of the transformations. In some cases, I would say even most cases, at least when you're dealing with Quarkus, we actually compile those classes on the fly. And so at the end of the day, we generate bytecode. That's a little bit slower, but it's still fine. We use a library that's called Java Parser to do our code generation, and we use a templated approach. So we don't just use velocity and load files from these as text files. We write Java source code. We load it using Java Parser, which is a parser for Java. And so we're at least reasonably confident that those files are valid Java source code. And then we use Java Parser to do replacement that are not just text replacements, but we actually use structured text replacement. We do replacement of the Java AST. And the reason we use this is also for scaffolding. It's a feature that is very experimental that I am going to show you right now. And we will learn more about the approach to code generation in Kogito in a future meeting, the same future meeting where we will probably see about, we will discuss about, we will see Kogito Code Gen more in depth. But I wanted to show you just a little bit about scaffolding and some of the code that is being generated for troubleshooting. It could be useful for troubleshooting. Here be dragons. So don't rely on anything I'm saying here. You can reasonably rely on the procedure, but not on the code that is being generated. So everything I'm going to say is lies. So scaffolding.
I need to say that I like the Charmander in there. Just needed to say. Yeah, something that is important to mention for those
Yeah.
who joined late is that this session is actually focused for people who want to contribute or understand more about how the internals of Cogito, of Quarkus extensions work, how we generate our code, how do we work with test reloading, hot reload and testings of those features. So note that this is not about how we use Cogito, but actually how it works on
Exactly.
it. Okay, so
Yeah.
please go on.
Yeah. This is mostly about internal. So if you want to know, how Cogito, how you could use Cogito, there's plenty of talks and recording that you can find, and there will be more in the future, I hope. This is just a different kind of presentation for this time. All right, so this is for scaffolding. This is actually a feature that you could try, but don't complain if it doesn't work, because it doesn't. So the idea here is that instead of generate, so usually, as you saw, generally what we generate is code that it's available, that is you cannot see. It's code that is generated in the target directory of your code. So we won't touch your source directory. So what I'm showing here instead is that there's a magic shortcut that you can use, a magic plugin that you can use here that will actually generate code in your source directory. And this is very experimental, and that's why I'm just showing it, for the record. And but I just wanted to show you, because it will demonstrate what I've been saying here. That is, the code that we generate, it's not magic, and it's something that we could actually write yourself, and it's no different than the code that we generate through Scaffold is no different than the code we actually generate for internal uses. So as you can see here, we have the code generated in the target directory that looks like this, and we have the code that it's been generated in the source folder, and it looks like this. Yes, it does look the same, because it's the actual same code, because we just changed the path to make it available to you. And the idea is that at some point we'll make available, we could make available this feature for you, so that you can actively customize the code that we generate for you. But this is very experimental. We haven't really decided the future of this feature. So if you're interested in that, please raise your hand, contribute, and take a look. And troubleshooting. Well, I've already shown that, but let's switch back again once more. So even if you don't use scaffolding, I should probably increase my font size, right? So if you switch to the target folder, you can find all the code that we have generated. So in case you have some error when you develop your application and you have an ugly trace, we usually try to hide those and produce better error message, but it could happen. So if that happens, here we have code that you can actually read. This, for instance, is the code that we generate for processes. And as you can see, it's pretty readable code. Again, you should not rely on the code that is written here to develop your own application. This is our internal API. This is not for public consumption, at least for now. But this is just to show you that is nothing magic. This is something that you could also write by hand. And this is useful because you could put a breakpoint here. For instance, here, if you have some null pointer exception, you could put a breakpoint here and debug it. And I believe that's pretty useful. All right. Oh, my favorite, GraalVM native image. So you probably have heard a lot about this. If you're familiar with the topic, if you're interested in native, in GraalVM, GraalVM is a project that is about polyglot programming. Actually, it's about mixing different languages and making it work great together. But one of the features that became most famous is native image compilation, and sort of an accident, a historical accident. But people are very interested in that, and it's one of the killer applications, if you will, of Quarkus, in some sense, the thing that you can actually generate native image. And right now, this is through GraalVM. So how does this work? It works through this so-called closed word assumption. So it has some limitation. So how it works, you already know. You just do Maven package through Quarkus, and it will be a native image. But there are some restrictions, as you know. If you ever try to write an application from scratch, you might have heard about the closed word assumption. What's the closed word assumption? Glad you asked. You probably know already, but you might have heard about this. You have heard about this a lot of times. So there are limitations on reflection. You cannot just do load class and being any class that you might think of. You have to declare that class beforehand if you want to build a native image. And you cannot do at all dynamic code loading. So you cannot do class loader define class. And this is not load class. It's the one that you pass a byte array. So it's the one that you usually write when you're actually defining a class loader, a custom class loader. So this is forbidden, and it doesn't work. It raises an error. The reason why there are these limitations is to allow some more aggressive optimization, like code pruning. We're going to see that in a bit. But the idea is that the GraalVM native image compiler does an extensive visit of all your code, or at least the code that is reachable, and that's very important. All the code that is reachable, and as it finds code that is reachable, it discards all the code that is not reachable. And this is in order to make the native image binary smaller, because it can dump and remove all the code that is not really needed. Another thing that you have to keep in mind, and this was very true with older version of GraalVM, now they have switched the default, is that static initializers were not lazy. They were evaluated at build time. Now I put this asterisk here in Quarkus, because this is a feature that you have to enable explicitly now if you use the vanilla native image compiler. But in Quarkus, this is actually the default. And in fact, you can leverage that. We will get to that in a bit, but I wanted to give you just that to make sure that this is understood very well. Native code does not prevent dynamic code loading. And if you are accustomed to do work with native compilers, with C or C++ or any other language really that deals directly with the native code, which we usually don't with jVM, is that you can actually load code dynamically by using dlopen, the system called dlopen. So through dlopen, you can actually dynamically load and link against, in fact, DL stands for dynamic link, against dynamic linking libraries. So SO, static object for Linux, DLL for Windows, and dylib for macOS, Darwin. So this is something that you can actually, for game developers, this is very much is very frequent. You have a running core, and then you have a portion of your code that gets compiled dynamically and gets reloaded automatically. And that's useful when you have a game where there's a lot of logic and you don't want to restart the application every single time. So this is not specific to jVM or dynamic languages. Like Python can evaluate scripts dynamically, JavaScript and all the dynamic languages can do that. But this is not specific to those. You can also dynamically load binary code, the native code. Another thing that is very important is that when you run in jVM, on a jVM, nothing prevents you from doing code pruning. It's just something that we usually don't do, but you could actually do it. And that's actually very frequent on a mobile platform like Android. Android has very strict limitation on the size of your code. So people are using tools like ProGuard, which is a static analysis tool, very similar to what happens for GraalVM native image compiler, that analyzes your code and discards part of your bytecode that are not necessary for running your applications. It could be like you depend on some library, but you only use parts of that code, and you do not need the entire library. This is I'm calling pruning. It's actually very known in the JavaScript community as tree shaking. And that's the exact same thing. Maybe they use tree shaking because that happens at a different level. It's not at the bytecode level, maybe at AST level, but it's basically the exact same thing. They just discard code that is not really used at runtime. So they make their JavaScript code, their script code smaller. And they minify, they also do pruning. So these are not things that are necessary to have a fully working native compilers. There are other compilers that may not have these limitations. These are just choices of the native image compiler. Another thing that I wanted to show you here for your information is that when you use the native image compiler, you can also configure that. So the Quarkus extension gives you ways to configure the native image compiler through APIs. Like you can announce, you can communicate to the system that some class is necessary to be available for reflection, and you saw that we used the reflective class build item for that. But you can do the same through a configuration file that is under this path and inside this file, private file location. So you can actually configure that even if you're using vanilla GraalVM, but it's much more convenient to use our extension. Another feature that sometimes you might see in the wild, and we actually use that in our Quarkus extension. So I mentioned that Quarkus extension have a deployment part and a runtime part. This goes in the runtime part. But this is not really a class that's used at only partially used at runtime. What this class does, if you look closely, this is named, there's an annotation there that's called, that says target class is ASM accessor optimizer.class, and then there's my class implementation. And then there's a method with a substitute annotation. So this substitute method, it's actually mimicking the signature of a method that is contained in the class of the annotation. So ASM accessor optimizer.class. The reason why we're doing this is that this is a third-party library. It's not really third-party, but it's a library that outside the code base of Kogito. And this is a fix that we had to do in the past to work around some issues in the native image generation. So instead of fixing or changing that library, we actually did that in our code base. This way we could left we could left the library untouched in its own repository without customizations that are required for native image, and instead keep all of the changes on our side. Of course, if you control all of the code, you could also make changes on that end. It depends on your case and your use case and the situation. So I was mentioning runtime initialization. The way Quarkus extension makes this feature available is through bytecode recorders. So bytecode recorders are basically another kind of bean that you can inject, and you annotate with the record runtime init your class. And if you do this, then you can invoke methods on this class, and these will be executed in a static initializer. Now, this is a lot of fancy words, and it's probably a bit complicated to understand if we don't see an example. And in order to show you an example, I wanted to use vanilla GraalVM because it's easier to understand probably in isolation. So suppose that you have this bit of code. It's a bit strange. It's an hello word, but it's an hello word that's written in a different way than usual. So I'm gonna ask the audience or Karina or Alex to answer here. So what do you think it's gonna be printed to screen when I run this application?
Hello world.
Exactly. So that's correct. What's gonna happen is that you're going to see first hello and then word. So what happens here is that first the static initializer is hit, and then the main method is invoked. Now, yay! So that is correct. This is pretty trivial. Why are you asking that? Well, glad you asked. Because when you build through native image and you use the flag to initialize at build time, which again was the default at some point in the in GraalVM native compiler and GraalVM native compiler, but it's still the default in Quarkus, you will see this output. And this is very interesting. You can see inside the output here, hello. And this is happening because the initializer is actually executed at build time. This is a very powerful feature because basically means that any code that you put in a static initializer, it's actually doing some sort of code generation for you in a way. So you don't really have to generate code to have this kind of optimized code path because you can just initialize stuff in fields and static initializers. So in fact, confusingly enough, if you executed this application, it no longer prints hello and it just says word. Now, this is interesting, and I know that you guys are going to be pretty much tired at this time, but we reached 1 hour, and I swear this is the last few slides I'm going to show, but I found them interesting because it's a bit of code that it's a bug that we actually faced in our code base. So here, what you see here is that we had this private static final field that we defined there in order to use that particular feature of the native image compiler. The reason why we didn't use the Quarkus feature is to generate code that worked both in the Quarkus ecosystem and in Spring. And in Spring, this is just a regular, in general in jVM mode, this is just a regular initializer for a static class. But in Quarkus with native image compiler, it will be initialized at build time. Now, this is code that seems pretty, simple. Like it shouldn't hide anything dangerous. But actually, what happened here is that a build time did blew up. And that was a nasty bug to understand. But as soon as you understand what's happening under the hood, it's actually pretty obvious. So what's happening here is that if you feed the read resource method, well, the code here does not compile, but bear with me, please. If you feed the read resource method with for instance, a file input stream reader, so a file input stream reader under the hood. It's using a file handle. So what's happening here is that you're instantiating an input stream reader with a file handle at build time. And then at runtime, you will try to use that file handle. But remember, your build time is a very separate phase than your runtime. You're no longer doing things at startup time. You're doing things, so remember, startup time versus compile time. You're no longer doing things at startup time. You're doing things at your build time. So it's two different, completely different applications. So your file handle does not exist anymore, is invalid, and so your application blows up. So what could you do? This is something that I wanted to show because it's another trick that we have up our sleeves when we use GraalVM under the hood, of course, of Quarkus. So we can check this particular property to see if we are running under the native image compiler. And what happens here that this property is being resolved at build time. So at build time, this will be always true or false. Actually, this is build time, since this is a native image, will be always true, right? So another thing that will happen magically is that this branch, it's always false. So as you know, as we said before, the native image compiler is able to do aggressive pruning. So because this is always false, it can fold the code. So it can erase this bit of code. And so what it's inside your native image will end up being just this bit of code. And this is one of the feature. So this is one of the tricks that we use. And this is very important to understand because this is some change that happened in our code base. And that's why I wanted to raise the issue here, because it's not that evident. It's not that easy to see. Once you see it, it's obvious, but you have to, grow accustomed to it. If you change the field to a method, what you're now doing is invoking that method at runtime. So you're no longer guaranteed that that property is resolved at build time. And so this code might not be pruned. The reason why I'm using the conditional is that personally, I don't know every single detail of how the GraalVM native image compiler works, and it changes at every release. They do different optimization, they fix bugs, and so something may change over time. So this does not mean this may change in the future, but you're reasonably safe assuming that this may not do what you expect. So conclusions and last words from me. What if you want? So I hope you learned something about this. So you know how to reach Kogito. There's the channel that you're looking at. You know our Twitter handle. You know the Zulip, and you can just reach cogito.key.org for all the other links. But we're open to contribution of any kind. So if you don't want to write a Quarkus extension, or you don't want to help with the Quarkus extension because you think it's too far fetched from you, you can contribute documentation, you can contribute examples, you can contribute issues. And I hope, and you can, of course, hang out on the Zulip channel alongside with the developers and have fun with them, and of course, help other people out. And I hope that this presentation gave you some idea on how you could debug the extension, so to provide better better issues, better bug reports, and maybe try and even yourself try to fix the bug. And that is all.
Thank you. This was awesome. So if you have any questions, feel free to drop in the chat. Eduardo, I think this is really nice, not only from a developer perspective, but also for the users who, like you said, need to troubleshoot. Because whenever we get errors on those codes, like there's those generated codes, now we know how to
in general, we should strive as Kogito developers to limit the cases when that happens, but unfortunately it still happens sometimes, and that's a good way to debug.
Yeah, it was awesome. It was new to me, the scaffold, the feature that you just showed to us. It's pretty useful for exactly looking into under the hood what's going on, because when generated code blows up, it's always complicated. What's going on? Like, wow. It's awesome.
Yeah, we're working on the code gen part a lot, and we're also working a lot on the redefining the programmatic APIs, which is something that we still deem something of a internal detail, but we really want to be able at some point to say, okay, this is the code that we generate, but you can also take a look at that, and probably you can interact with that more openly. And in the next presentation, I'm not sure if I will present that, but there will be a follow-up presentation when we will go into the details of the Kogito CodeGen procedure, and there we will see more about what's happening there. The reason why we're deferring that is that we're changing a lot of that to make it more clear, easier to understand, both from the point of view of the code that we generate, but also from the layout of the code. I mean, the modules. There will be more modules, and it will be much easier to understand what's happening there.
That's awesome.
Awesome. Great. So thank you, Eduardo, for your time and for all this great content that you shared. I have shared the link with everyone here on the chat. I will also put the link on the description of this video for you to see the slides that he shared, because, getting those tips right there when you need, you need to bookmark those slide decks. So thank you, Edu, for everything. Have a great day.
Thank you. Thank you for everyone that joined, and thank you for having me, Karina and Alex.
And thank you
See
very
you.
much for unpacking all the black magic behind the scenes.
Thank you.
Nice.
Bye.
Thank you.
Alex, for next week, what we will have is everything about DMN engine with the great Matteo Mortari.
Exactly. We will have our engineer that responds for the DMN engine here with us, going deep dive into DMN. That's going to be awesome.
Yes. So great. Thank you for being here with us today. See you next week. And bye bye. Have a great day.
Bye-bye.